and it will require a lot of experience on your part, expertise to understand this. So we would be just going through the gist of the theory for the time being. I just discussed in brief in the first class about this thing. So basically, the problem was with, just a minute. Yeah, the problem was with the fact that light was a wave. I mean, Huygens said it is a wave, and Young's experiment could prove that. Okay, now the question was that if light is a wave and light is traveling like this, I mean, this is the very common notation which people use for wave. Whenever we say wave, we just draw something like this. Okay, I haven't drawn it from any scientific perspective. Okay, just like this. So how can a wave travel with no medium, isn't it? How is light traveling without any medium? And this is true. Light is traveling without any medium because if you just put a torch inside a vacuum, you can see the light coming out. On the other hand, if you put a source of sound inside a chamber which is evacuated, you won't you won't hear the sound. Okay, that's why the PCO booths, if there are any in any part of the country or the world, they are covered with glasses, so as to ensure that sound doesn't come out. Though that is not the perfect vacuum created, but the thing is that they require a material medium. So to answer this came Maxwell. When he was working with his electromagnetic theory, Maxwell's equations, these things I think you will be studying in the last semester. They are four in number. So these equations contain the entire electricity and magnetism. That is what Richard Feynman said. Okay, so he Maxwell could confirm that electric field and magnetic field are continuously dependent on each other. Okay, no problem. The surprise was that when he calculated the velocity of an electromagnetic wave, the formula was this. You know these things, at least you have heard the names. Mu zero is the free space permeability. Okay, that is approximately 8.854 10 to the power minus 12 SI units. The unit is big, large. I can't follow up accurately. That's not important. The value is important, and this is the free space permittivity. That is, permeability has to do with magnetism, and permittivity has to do with electric fields. Okay, that is how much would be its value? To remember that, you can remember that 1 by 4 pi epsilon 0 is 9 into 10 to the power 9. That's a trick to, not trick, that is how it's easy to remember. It is approximately 4 pi into 9 into 10 to the power 9. Okay, that is the value of epsilon 0. So it's 1 by 4 pi into 9 into 10 to the power 9. Fine. So what happens if you put these values here? Is my screen visible? Is everything fine?
Yes, sir.
Okay. Simply put the values here. What happens to the velocity if I put all these values? 8.8. These are approximate values. Can someone quickly calculate this value? How much it is coming? SI units. Yes, you are getting the value of epsilon 0.
So I got 1.13 into 10 to the power minus 11.
Okay, so put the value in this expression, whatever you got. Everyone do this. Oh, sorry. I'm extremely sorry. This is the value of epsilon 0. That's why I got confused. Yeah, how much you are getting? Shubhayu, how much you said? This thing?
So I was getting 1 point something. I forgot.
No. You're not supposed to get 1 point something. Sorry. Actually, I'm so got confused. This thing is 4 pi into 10 to the power minus 7 SI unit. And epsilon 0 is this. So you will get epsilon 0 equals to 8.854 10 to the power minus 12. Sorry, I mixed the two terms. So here you put 4 pi into 10 to the power minus 7 and the unit is in meter per second. So let us try to multiply this thing. This would be 10 to the power minus 19 and calculate the value, the magnitude. 8.85 8.854 into 4 into pi. So I am getting 111.6 approximately. Okay. Now I have to do the square root of this one. Is everyone getting it? Are you getting the value? Hello,
Yes, sir.
hello, am I audible?
Yes, sir, you're audible, sir.
Yeah, yeah. So what is this value? 8.854 into 4 pi.
So 0.002496.
This entire thing is no one
So,
having a scientific calculator around?
so I'm getting 111.2626.
Okay. So do this thing, the entire calculation now you do. 1 divided by root over this one. This is the only exercise you need to do here. This topic.
So it's coming 400 point something.
The total answer.
Yes, sir.
Okay, let me check once again. 400 how much? Just tell me in terms of power.
So 400.641.
Into 10 to the power. So much confusion. So one divided by 1 divided by root over 8.854 into 4 into 3.14 into 10 to the power. We have taken some value, maybe some value is taken low. Sorry, taken high. So how much it is coming? 3.9 into 10 to the power 8. Is this what you are getting? No, no, no. That may be the denominator with the square root. Okay. So this thing, if we take more accurate value of this epsilon 0, we would be getting very close to the speed of light. Okay. So this is your exercise. You try to use this value of epsilon 0 later on. That is this one you try to use 1 by 4 pi epsilon 0 equals 9 to 10 to the power 9. So epsilon 0 would be 1 by 4 pi into 9 into 10 to the power 9. So now try to calculate the value of velocity of EM waves. It's in air or vacuum. 1 by root over. This is the value of pi. This is the value of mu 0. So you can see 4 pi getting cancelled. Okay, go by this approach. Yeah, the unit is meter per second. So if everything is taken care of properly, this look like 9 into 10 to the power 9, and this 7 will go up. 9 plus 7, 16. Did you get it? Is it clear, everyone? We were getting a different value because of this, because of the approximate value of epsilon 0. It's actually 8.8542 or something. Is it clear, everyone? How did we get this?
Yes, sir.
Okay. So Maxwell said that these electromagnetic waves, they propagate in air with this fixed value always. Okay, that was 3.10 something. Hmm. That really was a strange thing. That why is it always all electromagnetic waves are moving with a fixed velocity only? And few years later, when Fizeau did his famous experiment, okay, he did a series of experiments first to detect ether, then to calculate the speed of light. He could find that the speed of light was very close to 3 into 10 to the power 8 meter per second. So it could be concluded that light is nothing but an electromagnetic wave. These two things confirm that light is an electromagnetic wave. Now, why is this wave not requiring a medium to travel? Because it is not a mechanical wave. It is not a mechanical wave. Mechanical waves like sound waves, okay, they require the material of the medium for propagation. Okay, I can give the recording to Sudhanshu later. Uh, so that is the reason why light doesn't require a material medium. Okay, he can rejoin, no problem. And when you will be studying in more details, if we draw the three perpendicular directions, then it will be seen that light is a result of two mutually perpendicular electric and magnetic fields. That is, if the electric field is along this direction, that is, it is oscillating up and down about the y-axis. Sorry, what should I say? It's in this plane. Okay, it is in this plane. And if something perpendicular to that is also oscillating like this thing, that is, you can think like this. Say it is the magnetic field, it is the electric field. So the electric field is along the plane of the paper and magnetic field is perpendicular to that. So resultant of this one would be the electromagnetic wave, which will propagate in a direction perpendicular to both of them. Hmm. So this was confirmed that light is a electromagnetic wave. Is it clear, everyone? See, nothing much will be asked in this chapter from this topic, like only a brief discussion they may ask, and to you can show the value of velocity of the electromagnetic wave in a vacuum, which is equal to that of light. Clear, everyone? I think, yeah. That's fine. So the next topic, that is more important, and in optics, at least in our syllabus, we would confine ourselves to the wave nature of light. Okay. So the next thing is Huygens principle. That will give us a more detailed view into the theory of Huygens wave theory. Hmm. I think you have studied this principle. So there is an important concept. Before I state the principle, you have to know something called wavefront. I think you have heard this name before. Wavefront. Yeah. Can anyone tell me what do you remember about wavefront? Anyone? Right. Yeah, that word is very important, locus. So what is locus? Can anyone tell me what is locus? What is the closest word to locus? No, not a point. No, 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 not like circle is locus of a point. That is, it is like a path or shape. Okay, which is traced out by a point, not by a point, by points which bear some relation between them. Like suppose I have a fixed point here. I am calling it O. I am drawing a point P, which is at a distance, say 6 centimeter from O. Now I am drawing another point here Q, which is also at 6 centimeter from O. So if I take all the points which is at a distance 6 centimeter from O, like if I get here, here, here. So if I take such points and if I join them, what I will get is a circle. So that is the locus of this of these points. Okay. Are you getting it? So circle is the locus for these points. So here wavefront, what does wavefront mean? Wavefront is nothing but it is the locus of the points which are in same phase, that is same state of motion in a wave motion. Very simple example, let me give you. Suppose it is a wave. Okay. Suppose it's a mean position. Let me draw another wave like this. Say another wave. So now let me look into the crests. Crest means the points which have the maximum displacement. That is this point. Crest and trough is the opposite. So these are the crest for the first wave. These are the crest for the second wave. These are the crest for the third wave. Are you getting it? What I'm trying to say? Any doubt, anyone? Am I audible?
Yes, sir.
Yeah. So did you get it? Crest. Why am I pointing the crest? Because see, crest means the points where the particles are at the highest amplitude. So these crest and these 2 points have the same relation, that yeah, these 2 points are having the highest amplitude. So I can call these 3 points are in same phase. If I join them, what I will get is a wavefront. My drawing is not that accurate. So these are wavefronts. Okay. Now why are we using the wavefront thing? That will be very evident soon. Sorry. So I gave some questions last day regarding wavefront, what type of wavefront it would be. So let me give a very simple example. Suppose I have a source of light, say yes. It can be a bulb, anything. So usually what we do, what we know that usually what we draw regarding light, we draw light waves. So we know that if the bulb is say here, so it will let out source, it will let out light from all directions, isn't it? Light will go in all directions. I can draw more waves, infinite number of waves. That is how we were denoting light so far. Clear, everyone? Any doubt? I'm drawing rays. I'm drawing light in terms of rays. Ray diagram we drew in our school days for geometrical optics. Convex lens, convex mirror, concave mirror. Clear? Please respond yes or no. I won't be able to understand if you are getting it or not. Yes or no? Okay. Now I just want to draw the wavefront for this one because that would be required soon. So how to get the points of same phase? So let after time t we try to calculate the distance traveled by light. Is my screen getting stuck? Why can't I hear everyone loud? Okay. So we want to see how far light has gone after time t. After time t, I'm assuming that at t equal to 0, I just switched on this source. I just switched on the bulb. So very simple. What is the formula of distance? Distance means what? Speed into time or velocity into time. So what is the speed of light in air? C. And what is the time? T. I am looking into the picture and trying to calculate that after time t. Suppose after 1 minute of switching on the bulb, how far has light gone? Are you getting it, everyone? Okay. So suppose from here, CT is a distance, a 5 meter. So here to here say A. So AS is equal to CT. Now needless to say, if I draw it here, BS will also be equal to CT. Same distance. So similarly, if I go on drawing, I would get something you can understand. The underlying shape is getting very evident. So these are all points which are at the same distance from S. That is equal to CT. So what is the locus of these points? Can you tell me what is the locus? If I join all the points, what is the locus? It looks like a circle. It is actually a sphere because yeah, I have drawn the picture in 2 dimension. Actually, in 3 dimension also light is coming out, isn't it? Light is, some rays are going upwards, some rays are going downwards. I mean, above the page and below the page. So the locus would be a sphere. It's very hard to draw a sphere like this. I can shade it, keep the 3D effect a little bit. So after some more time, what will happen? I will get a bigger circle because the distance will be more. So when we have a point source of light, hmm, the wavefront would be what? Spherical. By point source, we mean that one that radiates, that gives out lights in all directions away from it. So this was one question that I asked you last day. So this is how we get spherical wavefronts. That is this same picture. I can visualize it like this. I have a point S source, and that is how the waves are propagating outwards. Okay, so this is the wavefront picture. Wavefront picture. Clear, everyone? Clear, everyone? Fine. Now the second is, suppose what if what if the source of light is at infinity. Infinity means far away from us, like the sun. Or if the source of light is no, let me not write that, the second part that we need to understand. Yeah. So when light is coming from infinity, we know the rays would be parallel. Okay. Because the thing is so far away from us, it appears that the rays are coming parallel from the source. Source is at infinity. Source is at infinity. Infinity is at a very large distance from the observer. So similarly, I want to draw wavefront for this one. So what I will do, I just calculate Ct, that is the distance traveled by light at a particular time after a particular time. Say this is the distance traveled by light at time t1. This would be the distance traveled by light at time t2. That is from here to here. Suppose I'm observing from here. From here to here, light has traveled this much distance. From here to here, this much. Or not from here to here, from the source. Okay. Suppose after time t3, the distance traveled by light is this. So you can see if I join the things, I'd get a locus, which looks like a straight line. But keeping in mind that the scenario is in 3 dimensions, these would be planes. Okay. Is it clear? Is it clear? Khushi, Neha, I can't hear anyone.
Yes, sir.
Okay. So what we can conclude, if you have parallel rays, for parallel rays, the wavefront would be plane. That is, we call it planar wavefront. That is number one. Number two, that is evident from here, is that you can see the wavefront is always perpendicular or normal to the rays, isn't it? See this one, if you view it from here, suppose these are the rays, this is the wavefront. It's a plane, isn't it? It's a plane, but it is at right angles to the rays. Are you getting it? That is, you can imagine the way. is traveling in terms of planes. Clear? So rays and wavefront are, I mean, if you want to construct them, you have to keep in mind that wavefront and the rays would be at right angles. But that doesn't mean they are moving at right angles. Wavefront is also moving this way. Rays are also moving this way. So this is for your construction purpose. If you want to construct wavefront out of rays. Now the third kind of wavefront is also necessary. At least let us know when we have a long or elongated source of light. What happens then? Like a tube light. That is, it is long and is radiating light from to all directions. So light is going everywhere. Here also at each and every point, light is being given out. That is, you may think like it is nothing but a collection of infinite number of point sources, all which are collinear on the same line, same straight line. So at a particular time, if you try to draw the wavefront, what you will get? You will see here, it's like this. Here it would be like this. Here it would be like this. So what you will get? A cylinder, isn't it? These type of wavefronts are called cylindrical wavefronts. You would be doing this thing in application of Gauss's theorem. When you will calculate the electric field at a point due to infinitely long current carrying conductor, lambda by 2 pi epsilon 0, you will get. Lambda is the linear charge density. There also you will get a similar kind of thing, analogy. So let me draw a more detailed picture. Suppose we'll study this very soon, okay? Young's experiment. There is a very small slit, okay, small opening, and I'm sending parallel rays from here. Hmm. What will happen after that? What happens? We all know that this S behaves as a point source. Let me try to draw this thing in the wavefront picture. That is, suppose I have a barrier. Let me try to draw the 3D picture. Suppose I have a wall like this with a very small crack, small but uniform crack, very fine crack, which we can call a slit. If we try to draw analogy from here, are you getting it? There is a gap between the two things. Clear, everyone? This thing. Now see, parallel rays were coming. Now by this time we know parallel rays means what? Plane wavefront. So I can visualize it like this. Many planes are coming here. Okay. It's very difficult to draw under the camera. I don't know how is it looking like. Mm, Okay, so many wavefronts are coming this way. You can do this experiment at home using water as well. So see what is happening here. Here it can't proceed as a plane wavefront anymore. Instead, what it will look like, it will try to go out. I mean, leave this slit, but in front of a, in form of a cylinder kind of thing, half cylinder. Okay, did you get it? So see, now there's a confusion. Many people say that if we draw this thing in 2 dimension, so it would look like this. That is, plane wavefronts are coming this way. They are coming, and from here they are giving out spherical wavefronts. Okay. Now it depends whether you want this dimension of the slit or not. If you want to study if this, I mean, how long or how short your slit is, if that matters to you, then yeah, these are cylindrical. If only this slit, only this gap matters, only this much gap matters to you, then it is spherical wavefront or circular wavefronts. Spherical actually. Okay. So it matters which one is more important to you. Like in our treatment, we are only pleased with the dimension of the slit. How long, how short it is doesn't matter. Hmm. So we'll be dealing with this kind of wavefronts in the future. Sorry. So I think everyone can now at least draw wavefronts. These three types of wavefronts. I wanted Aarti to join this class. She made some uh, incorrect answers last day. Maybe she was confused. Anyways, so before I leave, I'll just simply give you what Huygens principle is, because by this time you are clear with the wavefronts. So the principle doesn't have a concrete statement like this, but the gist of the principle is that you can write in the exam like according to Huygens principle, comma, then you go on writing like this. Don't put anything within inverted double inverted comma. That stands for quotation. And whenever you are putting something under this thing, it has to be exactly what the speaker said. Okay, you can't modify anything. Hmm. So better not to take risk. You just say according to Huygens principle, comma. When you put a comma, it means you're writing you're telling everything in your own words. So what it says that each point of a wavefront is a source of secondary disturbance. That is I made a wavefront, say this one. It is saying that each and every point on this wavefront, that is all points on this wavefront, they act as source for secondary disturbance. That is, they act as a source of more waves, and these wavelets, that is the waves that come out from each and every point, they are called wavelets because they are not the actual wave. They are coming from a part of the wave. That's why we call them wavelets. Okay. Sometimes we call that secondary waves also. Wavelets emanating, that is moving or progressing or traveling from these points spread out in all directions with the speed of the wave. That is, this from this point, waves are coming out in, wavelets are spreading in all directions with the same speed as that of the wave itself. From here also, in all directions, and if we draw the wavefront, it is like this, and so on. So what will be the next wavefront? That is the question here is, after say at 9 a.m. the situation is like this. What would be the situation at 5 past 9? That is, in a future time, how would the wavefront look like? So the envelope of these wavelets gives the shape of the new wavefront. That is, basically, this principle tells us that how or why this wavefront came after this one. Why not some other shape? Hmm. It looks pretty obvious there won't be a change of shape, but why it happens or how it happens, we'll be discussing tomorrow. Okay, any doubt? Anyone? Any doubt? Any confusion? Okay. Okay, so this chapter, they have said only Huygens principle. So next day we'll be discussing the principle in more details, and we'll see a few applications, like how we can prove the laws of reflection and refraction using this principle. You have done this thing in your school days, I think. We'll just recapitulate, and here we'll try to understand it in a more elaborate way. Okay. Okay, thank you then. If you don't have any doubt, let's meet in the next class. Thank you, everyone.
Thank you, sir.